Right, so we'll do the second half of structure and bonding. So we're going to start with bonding in metals. So similar to electrostatic forces, or similar, sorry, rather to ionic structures, these are held together by electrostatic forces. So we have our positive atoms, they are generated by the metals. And then when the metal is in the metallic structure, it gives away some of its electrons. So if we've got potassium, each potassium atom would give away one electron to C delocalized electrons. If it was magnesium, it would give away two. So once the electrons have been delocalized, we get a sea of delocalized electrons. This is kind of like a negative glue, if you will. And these negative electrons hold the positive ions together by electrostatic forces. Because it's very, very regular, we get a crystalline structure. We quite often don't get to see the crystalline structure of metals, but metals are, in fact, crystalline. The electrons do not belong to a specific nucleus. The electrons are delocalized. They're just around. They do not belong to any particular atom. So, if we were to look at some metals, you can actually grow crystals, and it kind of makes it more obvious. So this is bismuth. Bismuth is quite a famous metal for having these very, very regular crystalline patterns. But because we have this regular repeating pattern, that's how we get these crystals. So if we're looking at our atoms individually, we're trying to think, why don't they just fly apart? So if you've got loads of positive nucleuses next to each other, why don't they all just repel each other and leave the material? And like I was saying, it's because there's electrostatic forces between the sea of delocalized electrons and the nucleuses. So we have, every time there's an electron near it in the sea, we get that electrostatic force. And it's the electrostatic force that holds them together. So unlike in an ionic structure, we had electrostatic forces creating a high melting point. With our metal, again, we have these electrostatic forces. They again need a large amount of energy to overcome. They need that large amount of energy to overcome. We get a high melting and boiling point. So the vast majority of metals have a high melting point. You do get some exceptions, but it's the vast majority are relatively high melting and boiling point. So these metallic structures, they're held together by these strong electrostatic forces. They make it very, very hard. They are hard materials, and they normally have very high tensile strength. And it's because of these electrostatic forces. If we have things like magnesium, which is 2+, we can presume that there is a greater amount of electrostatic forces, purely because there's more electrons in the sea of delocalized electrons, and there is a 2+ charge, so there's a bigger difference in charge. So we could presume magnesium has a higher melting point than sodium, because there are these increased amount of electrostatic forces and increased strength of electrostatic forces. So these giant metallic structures, they are in regular rows. So if you were to get an electron microscope, you'll see that the atoms are in rows. And these rows give it two very, very specific properties. The first one, we've got malleable. So malleable means that you can change its shape without it breaking. So you can bend metal and it won't break. You can quite often bend metal hundreds, if not thousands of times, and it doesn't break. It's very difficult to actually break metal. The next thing we have is ductile. So we can stretch a metal into a wire. So when you're producing wires, all they simply do is they simply pull at it, and it'll get thinner and thinner and thinner and turn into a wire. So you can draw it into a wire. And both of these properties are because of these layers sliding over each other. When they slide over each other, the molecules aren't, or rather the structure is not trying to break apart. If you successfully slide across, the electrostatic forces are still there. You've not broken anything. You've not overcome any bonds. You just kind of rearranged where the atoms are and where the electrostatic forces are. So simply by sliding over, we get this malleable and ductile. What we also have is these electrons that are free to move. When we had an ionic structure, that ionic structure, if it was dissolved or molten, had charged particles that were free to move. Your electrons are negatively charged. They are delocalized. They do not belong to any atoms. They can move. So what we have is we have electrons that are free to move. If those electrons are free to move and they are charged, they will conduct electricity. So by definition, all metals can conduct electricity. That's one of the requirements to be a metal. And that is because of this sea of delocalized electrons. You've got negatively charged electrons, or negatively charged particles, if you're being less specific, and they are free to move. So they can carry a charge from one side of the material to the other. So they can conduct electricity. These electrons can actually also transfer thermal energy. So if we have one electron that has a large amount of thermal energy, it's either going to travel through the material, because it's free to do so, it can move, or it can simply pass its thermal energy onto the next electron, and we get a very, very quick dissipation of energy. So not only do these free electrons mean it can conduct electricity, but it can conduct heat as well. So we've got two ways we can conduct. What we could also do is we could adulterate our metal. So we can mix our metal with something else. And what we can do is we can make alloys. So an alloy is a solid mixture, and at least one of the elements in there is a metal. So they don't all have to be metals. So one of the most famous alloys is steel. Steel is iron and carbon. So iron is the metal, carbon is non-metal, but we make an alloy. Other alloys are made of two metals. So bronze is made of tin and copper. And then we have dental fillings. They're often called amalgams. And you've got mercury, silver, tin and zinc together. So they're coming away from those because mercury is poisonous and you don't want it in your mouth. But there's a lot of ways that we can mix metals together, and they have very different properties because they do not have that regular structure anymore. So if we're talking about making steel, so in our pure iron, we have the layers of iron can simply just slip over each other, and they're very malleable. What we can do is, if we put in carbon, those carbon atoms effectively disrupt the pattern. So if we're trying to make these slide over each other now, they simply can't, because the carbon atoms are in the way. So we've disrupted the structure, and they can no longer slide over each other. They're no longer malleable. And the opposite of malleable is brittle. So when you try and bend it, it just snaps. So if you get high carbon steel, so things with power tools, you quite often get high carbon steel. And what will quite often happen, instead of bending, those tools will just snap in half. That's because once we've included our carbon, we can't slide over and change shape. Instead of sliding, the carbon will just effectively break the material. So we become brittle because we've adulterated it. So your alloys are quite often stronger and harder, but they are more brittle. So it's a payoff that you've got to choose the right formulation for your material. If you choose the wrong formulation, you will have the wrong properties. You might be too brittle, or you might not be strong enough. So if we move on to nanoparticles, so nanoparticles got triple only, but they are ridiculously small. That's kind of the idea of nanoparticles. They are extremely small, and things on the nanoscale behave very, very different. Nanoscale is between 1 and 100 nanometers, and a nanometer is a billionth of a meter, so extremely small. So you'll have to be able to convert between nanometers and meters. If you just do your nanometers times 10 to the minus 9 will give you something in meters. So 10 to the minus 3 would be 1,000, 10 to the 6 is a million, 10 to the 9 is a billion. And that's the order we're talking about. Very, very small. So when we have these nanoparticles, the main source, or the main thing that they're different, is their reactivity. Nanoparticles are extremely reactive. So quite often when we have large particles, they're not particularly reactive. So my example is always sugar. If we get some sugar and you just leave it there, if you try and set fire to it, nothing is going to happen. If we create nanoparticles of sugar, sugar is a very, very good reducing agent. It's very easy to set on fire. If we have our nanoparticles, what can happen is we can effectively get explosive mixtures. So we can get factories where they produce what they think is a relatively inert material, so it doesn't really react. They generate these nanoparticles accidentally, and then what can happen is, because they're extremely reactive, they create an explosive mixture and we get catastrophic results. And that's through these nanoparticles. So nanoparticles, when we talk about the safety of them, purely because their surface area is so big, we get a massive increase in reactivity. So we need to be able to calculate the surface area to volume ratio. It's relatively easy. So with cubes, you would always do the area of one face times by 6. And then for the volume, you'll just do one side cubed. And what we see is every time we get a smaller particle, the surface area to volume ratio increases. So if we're going down a magnitude of 100, we get a 100-fold increase in surface area to volume ratio. If we were going to our nanoparticle, which is a billion smaller than a meter, we'd get a billion times more surface area to volume ratio. And if we've got that much surface area, that's what's going to cause the reaction. So we've got uses of nanoparticles, so we just need to know some examples. So we've got self-cleaning glass. The glass itself can have these small titanium oxides, and these small particles of titanium oxide break down the dirt. They make them from larger pieces to smaller pieces, and the rain just helps them wash away. So we have these nanoparticles that can be very, very small, but they absorb UV light. If they absorb UV light, instead of your skin absorbing UV light, you can use it as a sun cream and it protects you. We can also have them as cosmetics or deodorants. So with our deodorant, we want to clog up pores. If we've got cosmetics, we want to create a smooth finish. So there's quite a few things we can do for nanoparticles in cosmetics and deodorants. Sports equipment, we can make lighter, stronger sports equipment that will give those using them an advantage. And ultimately, some things that are being used now, we have some medicines that can be used to deliver, or we can use nanoparticles to deliver things more efficiently, and we have cancer treatments. These are all uses of nanoparticles. So nanoparticles have been used for a long time, but ultimately they've not been studied a huge amount. So we've got these risks. The biggest one that I've experienced is we've got explosions and runaway reactions. So the reactivity of these things is immense compared to normal, because their surface area might normally be 1,000 times more or 10,000 times more. And if your reaction is going 10,000 times quicker, if it's an exothermic reaction, you might not be able to control that reaction. If you're releasing that heat, you might be producing gases, and that's when things explode. So we've got one thing is we might not be able to control the reaction, we get a runaway reaction. We've got atmospheric pollutants. If we're making these small particles, they're going to be carried by the wind. So things like carbon particulates from cars, we can make particles that are even smaller than those. So the small particles that we make, they can just go into the atmosphere. They might cause things like global dimming. So we've got atmospheric pollutions. And we've got easily absorbed into the bloodstream. These things like our sun cream, we've designed them to be tiny so they sit on the surface of our skin and absorb UV light. But if they are so small, if we breathe them in, they'll quite easily go into the blood in our system and then they'll travel around our body. So these nanoparticles are very, very easy for them to get into our bodies. And once they're in our bodies, we have not really done enough research on long-term exposure to these nanoparticles. So we may have long-term risks of nanoparticles because they get into our bodies, and we have the immediate dangers of these runaway reactions. Right, that's C3 done.